Yes, thank you for the opportunity to tell you a little bit about one of our projects, which is called Digital Twins for Large-Scale Heat Pumps and Refrigeration Plants, and it was funded by the EUDP. Today I want to tell you about the work we did on model-based online monitoring and optimization for a large-scale heat pump. And I'm presenting on behalf of my colleague, Jose Joaquin Aguilera, who's on parental leave. Yes. So in this work, what we were interested in was to develop an online model-based monitoring and set point optimization for a large-scale heat pump, which is affected by evaporator fouling. And that is interesting, as you can see here. Here we see the thermal resistance in the heat source, heat exchanger of the heat pump over the time for different periods in between cleaning of the heat exchanger. And you can see that the fouling builds up very differently in the different periods. So this will affect the current state of our system and thereby also the parameters that we can expect. So for example, which coefficient of performance we should benchmark against. Therefore, we want to know exactly what the state of our system is and have an online update. So we used a case study to develop these methods, and there was a two-stage ammonia heat pump, which uses industrial waste heat at 25 degrees as heat source and supplies district heating to the local grid. And it has a capacity of 2 megawatt heating. This heat pump is connected to our digital twin environment, as you can see here. So all the way to the left, let me find the pointer. Here we have the control system of the heat pump, so the local controllers and then the PLC and the SCADA, gathering all the information from the heat pump. And the data is then sent to the database server, which is owned and operated by the utility company that is also operating the heat pump. And then we can get access to this data via an API server. And we use a Python interface to do so. So we can have almost real-time data in our own environment. So we currently run this as an open loop. So we don't have the possibility to feedback into the heat pump at the moment because we're developing the methods, and of course the utility company doesn't want us to destroy the heat pump by accident. So let's have a look into this digital twin module here with colorful boxes. What is inside is presented here. So first we have a data collection and pre-processing part. So here we get the requested data in from the API server. And we have some data processing. So that involves cleaning of the data, calculation of additional variables, whatever we need for the services that we're looking at. And then we have this yellow box, which we call model-based services. So this is where we actually run the different modules that we need to supply different services with our digital. As a model, we use a dynamic model, which was developed in Modelica, and that is packed in an FMU and imported into our Python environment. So for in the end, then we have post-processing and visualization where we analyze the results and plot graphs, etc. So for the monitoring and calibration, what we do can be explained with this picture. So we have certain input variables that can be our measurement data, and it can be set point values. Then we have our model as FMU. So everything's packed in here. And then we have certain model parameters that we can change. We have the output variables of the model, and from that we can either directly get the KPIs that we're looking for or calculate them. So what we do is first we, or in parallel actually, we do an uncertainty analysis and sensitivity analysis and model calibration. So the uncertainty analysis has the purpose of letting us know how uncertain the predictions that we make using the models actually are. And then we use the sensitivity analysis as a pre-step for the model calibration. So we analyze how sensitive our target variables are on the model parameters. And then we only take the most sensible ones and use those to calibrate our model. And yes, we do that using different Python libraries. So here I should name the IETS Calibur and EBCPy from RWTH Aachen. So when we do the sensitivity analysis, this is the result that we get. So here we see the elementary effects that were calculated with the Morris method. And you can basically see different input parameters have different influence on our target variables. And then, for example, we see that this second parameter doesn't really have any influence. So we know that we can disregard that for the calibration, and thereby we can reduce the optimization tasks that we do when calibrating. Here we can see an example of the calibration results. So here we used a differential evolution algorithm, and as an indicator, we used the normalized root mean square error. And to the left, we see the results without calibration. And then to the right, we see that the match gets somewhat better after the calibration. It's not perfect, unfortunately, but we still need something to work on, right? So then we also looked into the model-based set point optimization, which has a similar workflow, but instead of changing the model parameters as before, now we want to change the input variables that we can tune. So these will most likely be set point values for the controllers of the heat pump. And we want to tune that such that even under variable boundary conditions, so for example, if we see fouling in our heat pump, then we want to tune the set point value such that we always get the optimal performance. And this was done using the PyMo package. Then we see an example of a possible result here. So the dotted lines is the not optimized behavior, and then we have the full lines where we used the NSGA2. So yeah, a form of genetic algorithm to optimize it. And here we see that we optimized on the intermediate pressure level set point. And we can see that is found that it should be a little bit lower, but not with a constant delta, so it changes. And then on the right, we see that this actually improves the COP during operation. During most of the time. Yes. Yeah. So from this, what we saw is that we actually have a potential to develop model-based online monitoring and optimization for these large-scale heat pumps. And we did that using existing tools, and it seems to work well. but we also see that the proposed framework has some challenges, and those are related to calculation time. That's of course because we use quite a complex model in our FMU to do that. And that was because we want to use that model for supplying further services. But that's something we're discussing, whether it would be better to have simplified models there. Yes, I think that was it. Let me know if you have any questions, and of course you're also welcome to contact Joaquin or me if you want to know more.
Well, thank you, Wiebke. Also very impressive stuff. One question right off the bat. Say, are you using these full-fledged dynamic models at every step of the genetic algorithm? Like, usually genetic algorithms, like they sort of spawn their offsprings, and then you need to evaluate everything. No. So you need to run the dynamic simulation at each of these, like during each evolution phase of the genetic algorithm. Is that right?
Yes. Yeah, we call the dynamic model every time, but yeah. Yes, that's also why it takes so long.
The most exact thing that you can do, but also the slowest probably.
Yes. Yeah. That's true. And I mean, for this application where we are fouling, of course, it's, I mean, it wouldn't make sense alone. The idea is that then we have like a calibrated, a very detailed calibrated model that we can use for, to supply other tasks. So then, of course, what could be interesting is when we think about improving the control of the system where we actually need the dynamics. Yeah. But we're also thinking about making simpler models for tasks where we don't need the dynamics, the very fast dynamics at least. Yeah.
And regarding the parameter selection for the optimization, say, why did you decide for doing this automatically? Because I would have expected this task to be like the job of an engineer, sort of select the parameters that you know that you need to tune, and then just set the algorithm up like that. But you went for the smart, like the AI version of it. Like, how come?
Yes, you mean this one, right, where we do the sensitivity analysis first?
Exactly.
Yeah. So I mean, of course, this sensitivity analysis step that doesn't have to like be recurrent. We only need it once for a plant, or maybe if we have bigger changes, then we could run it again. But the idea is a little bit that we can use the same framework and put it onto another two-stage ammonia heat pump. There are quite many of those, but they may be a little bit different. They are different in size and so on. So how exactly the target values are influenced will be, I mean, it depends on the system design, but it also depends on the task that we're actually looking for. So if it's only detection of fouling, we will have other target variables than if it is, for example, let's say detection of non-condensables in the condenser. So that is actually also some of the challenges that we're looking into how to choose these target variables such that they are representative for the case we have in mind, but hopefully also for many other cases that we might use our digital twin for afterwards.
So, very interesting and advanced approach.
Yes, I have a question. Something comes to my mind. It's related to the question asked by Felix. I think if we can use the input variables, I mean, if we can construct the relation between the output variables and input variables here using optimized decision tree, and we can, I think it's possible to get the contributions that you showed in the second in the next slide. Then with the range of these, yeah, exactly, with the range of these values for the inputs, I think you can easily define the corresponding range of outputs. Then you can do the sensitivity analysis using the machine learning model in straightforward way. I think. Maybe it's not clear.
I'm not sure I understood what the question was.
Here what you presented here is the importance of the model parameters on the KPIs, right?
Yes. Yeah.
Yeah. And you tried different scenarios to change all of these parameters using the Maurice method to have this plot. So you can, I think you can do it using machine learning if you train an optimized decision tree model. Then you can do it. You can obtain the same something similar to that with ranges of the variables. It will give you the ranges of the patterns itself. So the combinations between the variables that if you follow, you can be in this range of the KPI or in that range. You know, so you understand me?
Yes. Yeah. So are you saying you wouldn't use a model to?
Exactly.
No,
you can use
I mean, but okay. Yeah, you would dump the model and just look at inputs and outputs instead.
Exactly.
Yeah, okay. Yeah, that makes sense.
Because all of these
we
methods,
of course chose to like have white box or very light gray box model here as digital twin.
Okay, I understand.
Yeah, but I agree. That could also be done. I think yeah, it's a good alternative.
And also you can have like not only one decision tree, two decision tree cascaded, one between the input and the output, one between the outputs and the KPIs. So you can have like two cascaded models to I mean to understand the relations, the hidden patterns between all of these variables, you know.
Yes. Yeah. Like you did in or similar to what you showed before, right?
Exactly.
Yeah. I agree. That's an interesting approach.
Yeah.
A quick question. I couldn't see it, from the charts, but let's say that you managed to close the loop and send back or tune the controllers. What was the improvement? What is the benefit of the system once you optimize? Let's say overall, I don't know, % efficiency increase or cost or some other metric.
Yeah, actually, this is quite recent, so we haven't calculated yet how much we would save over a year. Okay. So I mean here, yeah, I mean, for now I can just show you this that we are actually achieving COPs which are higher, but we still need to calculate the overall increase over a year now.
Okay, thanks.